Hello, this is Eric, and we're doing Atomic Physics by Hand number 4, Optics, with snazzy new microphones. So today we're going to talk about focusing and collimating. So this is going to be in an ideal picture, so we're going to be talking about the ideal ray optics configuration. What this means is that we're going to have no aberrations. So either geometric aberrations or chromatic. So geometric aberrations come from the fact that we typically use spherical lenses. Chromatic aberrations come from using different wavelengths and how different optics will respond differently to that. We're also going to have no diffraction, which means no wave properties. We're also going to have no quantum. And let's see, what else are we going to have? We're also going to assume the index of refraction for all of our medium is n equal to 1, and we're going to be using thin lens approximation. So there's no thickness to our lenses. All right, so what does this look like? So we've got, use blue for our lenses. Draw an axis first. So we've got plenty of space. And here's our optical center line, our optical axis. And then we're going to draw a cartoon thin lens. Thin lens approximation. And we're going to have the rays from this lens come to a focus. And all right, no ruler, going to have to barehand it. So all parallel rays that come into this lens end up converging, so this is parallel collimated light. And we've got the ray that sits on the optic axis, which doesn't do hardly anything. And for clarity, we're going to have this guy on top, coming down. Okay. So everybody's coming to convergence here at the focus. And the focus sits at a distance equal to the focal length. So, as with everything when I teach, whenever I say something, it's, mostly true, but not completely true. So this focal length is a hypothetical object. It really exists only in the world of ideal lenses. In practice, the lens is going to have some thickness, and so you'll have things like a back focal length, or you have a working distance or an effective working distance, and that's adding in various layers of reality. So for instance, glass being thick will add some in. If there's housing or other mounting, will impact how quick, how closely you can get to your object. And where your focus is may not be where the object starts. So if you're looking at, say, a piece of tissue, your focus could be inside of the material rather than just on the surface. But we're going to start off with these things as pretty simple approximations. We'll cover the details of all those different terminologies with regards to actual lenses and actual systems in a later module. So the extreme ray here is coming in at some angle theta, and we've got a diameter D, and that is an awful D. So we've got this light, it's coming in with a diameter D, and it's coming to focus at a distance F away. So there's two different ways to talk about the optical performance of this lens in terms of its ability to gather light. So for instance, we could have a different lens that's sitting with a different diameter at a different focal length that's behaving equivalently. So for focusing. And so we want to have a language where whether it's a larger lens or whether it's a smaller lens, that we've got equivalent parameters. And there's two different ways that we can describe this. So we can use numerical aperture, or NA, and this is just equal to the sine of this angle theta. So this is coming from microscopy. So you'll often see objective lenses specified in terms of their numerical aperture. And right now we're assuming that we're in air/vacuum. Air has got an index of refraction about part in 1,000 higher than vacuum. So for most cases, and I want to emphasize most, you can treat the two as equivalent. Where you can't treat it as equivalent if you're, say, doing things out to 4 digits of precision, say like finding resonance wavelengths for doing rubidium spectroscopy. Then the difference between air and vacuum does matter quite a bit, because you'll be in the wrong ballpark if you don't have the settings correct. There is also F number, and that is the focal length over the diameter. And so this comes from photography. So if you've got a nice single lens reflex camera, you'll often talk about F numbers with regard to the lenses. And generally, the lower the F number, the higher the performance of the lens, which is saying that you've got a shorter focal length when compared to the diameter. So this ends up being equal to the tan theta of, we look at the slope of this line, so that's equal to the diameter over 2 divided by 1 over f. So this is f over d. So this is equal to 1 over 2 times the f number. And if we use the small angle approximation, NA is approximately equal to theta, which is approximately equal to tan theta, which is approximately equal to 1 over 2 times the f number. So the emphasis here is on small. The exact relation is that the numerical aperture is 1 over square root of 4 times the f number squared plus 1. So oftentimes the salespeople will use this formula and misrepresent the numerical aperture or misrepresent the f number of a lens. So that's something to be aware of, that they'll just say, oh, I've got the focal length, I've got the diameter, and therefore I can calculate the numerical aperture, and it's an overestimation of the NA. Not so much of an issue for, NAs of like, 0.1, 0.2. Big problem when you're talking about higher NAs and you're not getting the light gathering capability that you're expecting. Okay, so let's work through some examples of different systems. And so what I'm going to do here is I'm going to give you a focal length, I'm going to give you diameter, I'm going to give you f number and numerical aperture. And I'm going to fill in some of these, and you can use these formulas to populate the rest. So the first thing I'm going to suggest you do is calculate a formula for F number in terms of NA. And that's going to be one of these, it's going to be similar to this. It's just working out, you know, this tangent arcsine type thing. So you can do that manually. I prefer that. You can feed it into AI. That'll give you an answer. If you do feed it into AI, I would strongly suggest that you figure out how to validate that that answer is correct. Otherwise, you're kind of running around with the AI chainsaw and not quite sure what you're chopping down. Okay, so the first example I'm going to give is a Newtonian telescope. So this is, you know, those big educational style ones that might have a focal length of 1200 millimeters and a diameter of 254 millimeters, which is 10 inches for those of us brought up in the US. And that's got an F number of about 4.7. So on the other end are needle trap phase Fresnel lens. That's got a focal length of 3 millimeters. It's got a diameter of 5 millimeters. And that has an F number of 0.8 and a numerical aperture of 0.64. So it is a very large aperture lens. So a C230 aspheric, which you might use for collimating light out of a fiber, that'll typically have a focal length of about 4.5 millimeters in diameter, and that'll be operating with a numerical aperture of 0.55. So you can use that to figure out what the effective diameter of that asphere is. So calculate that, and if you're used to using these, take a look and see whether that's reasonable or not. So just as a ballpark, using this approximation, you'd say that, okay, NA of 0.55, we know that that small angle approximation is probably not that good, but it's at least a starting point. 2 times 0.55 is about 1, so that says that, our F number is going to be on the order of 1, which would say that our diameter is also going to be on the order of about 4 or 5 millimeters. So for reference, if we've got a multi-mode fiber, doesn't really make sense to talk about a focal length for them, but they'll have diameters on the order of 50 to 500 microns, and the light's coming out of them, it's diverging, and that'll typically have a numerical aperture of between 0.1 to 0.55 or 0.50 with typical of 0.22. So a single mode fiber, in that case, we're operating in the wave regime. Focal length and diameter definitely don't make sense. There's something called the mode field diameter, and that will be wavelength dependent. We can talk about that later. And those will typically have a numerical aperture of 0.12 to 0.14. And so if you'll notice, we typically have got an aspheric that's got a numerical aperture of 0.55 with this single mode fiber with a much smaller numerical aperture. In that case, we are substantially underfilling the lens. That means we're not clipping, we're not cropping, and we're getting a good image of what's going on here. You may be in an opposite situation where you want to overfill that lens. In that case, you're going to get a lot of potential edge effects and diffraction depending on the nature of this edge up here. If you've got just a hard edge, if you've got an apodized edge, or if you've got an irregular edge. Again, a topic for another time. So we've said that in this model, we're not talking about aberrations. As a quick guide for when this is important or not, if you're operating F10 or higher, then life is good. You don't really need to worry about aberrations at all. aberrations. And I can't spell. If you're between F10 and about F4, you need to think about where your surfaces are. But you're generally okay. F4 to F2, now you're going to need to be designing things. So using optical design software. F2 to F1, this is where things are getting hard, and below F1, we're talking about things that are very custom. So e.g. Fresnel lenses, etc., and aspherics. All right, hopefully this has been informative, and I'll see you in the next one.